In this section, we're going to focus on exponential decay functions. So our last section was on exponential growth, where we saw our values for our output either getting larger, whether it be positive or negative, but the whole idea is that they were getting larger. For exponential decay, what we're going to see is that our values are going to get smaller as our inputs grow. So it's going to be the opposite of exponential growth, and this is again going to be due to our multiplier b. For exponential growth, our multiplier b was a number greater than 1. In this case, the restriction is going to be that our multiplier has to be a value between 0 and 1. So again, it can't be anything around 0, because if we multiply by 0, we're going to get 0. It can't be equal to 1, because if I multiply by 1, the value is not going to change. So what we're doing here is we're looking for a number between 0 and 1. So the way I like to think about this is that when we have a b value between 0 and 1, we're looking for b values that might be, for example, like 1/2 or 1/3 or 1/4. So we're going to be dealing with fractions that are less than 1. We could also look at decimals. So I could see 0.5 or 0.25. But the key thing here is that we're going to be looking at multipliers that are less than 1, but also greater than 0. So our main purpose today is going to be looking at these exponential decay functions, but specifically looking at graphing them. So we're going to look at, again, just like exponential growth, the relationship between our inputs and outputs and what they look like visually on a graph. So again, what we're going to do is choose our inputs in our table. So I'm just going to choose some standard inputs of -2, -1, 0, 1, and 2. Again, I choose that because my middle of my graph is the 0 value, which is here. So I'm going to choose some values to the left and to the right of that 0 value. So now my function is 10 to the 1/2 x. So notice here that my a value, in this case, my a is going to be the first number, which is 10, and my multiplier is going to be 1/2. So the way to envision this is that we're taking the number 10 and we're going to multiply it by 1/2 as many times as my exponent would say. So now, by taking my inputs, all I'm going to do is plug my inputs in where x goes. So I have 10 times 1/2 to the -2nd power. I'm going to have 10 times 1/2 to the -1st, and so on and so on. And my goal for each of these inputs is to then simplify them and figure out what I would get for my outputs. So plugging those into my calculator, I would get 40, 20, 10, 5, and 2.5. And you'll notice here, exponential decay, again, is the values are going to get smaller. So you'll see it starts at a large number, and unlike growth, instead of those numbers getting larger, they're going to get smaller. And if you notice, the relationship goes from 40 down to 20, 10, 5, 2.5. Hopefully you recognize that those values are being cut in half as my inputs increase. So again, my goal is to take these numbers and plot them as points on my graph. The first one, -240, that one I cannot plot on my graph because my graph only goes up to 20. So I'm going to start my next value of -120, means I'm going to go left 1 and up 20, plot a point there. Then I have 0, 10, 1, 5, and then 2 and 2.5, and 2.5 would be between 2 and 3. So what I want you again to notice is even though as we plot these points, some of you might visualize this as a line, you should hopefully see that the spacing between the points is getting closer and closer. So what that is going to force this to do is, instead of being a line, it's going to force this to curve. And if I were to extend this more, we're going to see that's eventually going to curve downward like that. So it's an exponential decay function because the values are getting smaller, which is going to force this thing to curve downward. All right, same thing here, just different a and b values. So I have 6 times 1/2 to the, 1/3 to the x. So here my a value is 6. That's my initial value. My multiplier is going to be 1/3. I'm going to use my same inputs here of -2, -1, 0, 1, and 2. And again, I'm just going to plug in my inputs into my function where I see x. So again, I have my -2, -1, 0, 1, 2. I'm plugging in where x goes, where my input is. And then my goal is to evaluate these to see what I would get for my output. When plugging all these in, I should get my outputs to be 54, 18, 6, 2, and 0.67. So again, notice how I have my values starting very large and they're getting smaller as we go on. The relationship I'm hoping you can recognize here, starting at 54, which is the first value I chose. To get from 54 to 18, what we are doing is dividing by 3 every single time. Dividing by 3 is the same thing as multiplying by 1/3. When you cut something into a third, you are simply dividing that value by 3. So then plotting these values on my graph again, I'm going to start with the -118 just because I can't graph -2 and 54. So then I would have 0, 6, 1, 2, and then lastly 2 and 0.67. So that one would actually be 2/3. So it's going to be between 0 and 1, but a little bit closer to 1, okay? And we should notice the same pattern that as my values are going down in this case, you'll notice that the spacing between the points gets closer. So again, that's going to force this to become a curve, and it's going to curve downward in this case and leveling off at the end. So this, again, would be an exponential decay function. All right, so we're going to do the same thing here. I have -18 times 1/3 to the x. Only difference here is that my a value, which is -18, compared to the other two, is now going to be negative. But I'm going to look at what happens when my multiplier, again, is 1/3. So what we saw in the last example is that when my multiplier is 1/3, it's simply like dividing by 3. Okay, now in this case, I'm starting at 18, and notice my a value is negative. So let's see what happens when my a value is negative and I have a decay function. I'm going to choose the same inputs here. I'm going to choose my inputs of -2, -1, 0, 1, and 2. And again, my goal is to plug this into my function wherever I see x. So I would have -18 times 1/3 to the -2nd, and then I would fill out the rest. And then my goal is to simply use my calculator to evaluate these functions for those given inputs to get my outputs. And my outputs would be -162, -54, -18, -6, and -2. So then my goal is to plot these points. So notice that I'm starting at a very large negative number, -162, then goes to -54, which again, large negative number, then -18. So I'm going to start here by plotting the 0, -18, because I can't fit the other ones on my graph. Then I go to +1 and -6, and then lastly, +2 and -2. So it's going to look something like this. Now here I'm only able to plot 3 points, but again, you can see the spacing is getting closer together. Now the only difference here is that instead of my graph going downward and leveling off, you'll notice that it's going upward and it would level off here. What happens here is that we're starting, because it's a negative initial value, we're starting with a large negative value, and my numbers are getting less negative. Okay, so that's what decay means, is the values are going to get smaller. So if they're positive values, they're going to get less positive, and if they're negative values, they're going to get less negative. So the idea is, by value, they're going to get smaller over time. All right, last example here in terms of graphing. This is very similar to what we did with exponential growth. We have exponential decay again. I have 4 times 1/2, so my initial value is still going to be the value of 4. My multiplier is still going to be the parentheses, which is the 1/2. But now what we have in this equation is x minus 1 and the -2 at the end. Okay, so we're going to see again what those values are going to do. So I'm going to use some different inputs in this case. Normally I would do -2, -1, 0, 1, and 2. But just for the sake of this problem, I'm going to start at -2, but instead I'm going to do some different values, so -2, 0, 2, 4, and 6. Okay, my goal again is to plug each of these in where I see x. I'm going to show you the first one. I would do 4 times 1/2, and then in the exponent, instead of just x, I'm going to do -2 minus 1, and then outside I'm going to plug in -2. So my function that I'm evaluating is a little bit more complex. I do have the -1 and that -2 at the end that I now have to include. I'm going to do the same thing for all the other inputs. And then my goal is to evaluate each of these by simply using my calculator. In doing so, I'm going to get the following outputs. 30, 6, 0, -1.5, and -1.875. So plotting these then on my graph, I'll start with the 30. Again, -2 and 30, I cannot plot that. That'd be somewhere way above my graph. So the next one I would go 0, 6. So just know we're starting from somewhere way above, somewhere up here. We're starting at 6. Then I would have 2, 0. Now it goes off my graph, but 4 and -1.5 would be somewhere below my graph. and then 6 and negative 1.875 would be somewhere below. So I'm just going to sketch those points below my graph. Know that if my graph were to extend to negative 1 and negative 2, it would be somewhere around there. The idea is then is we see that the spacing between my points, again, is getting smaller as my inputs grow larger. What I want you to notice here is that my graph kind of shifted a little bit, and we talked about this with exponential growth. You'll see that my graph shifted downward, okay? So it shifted all the way down below my x-axis, and that shifted downward because of the minus 2 at the end. That's going to shift it downward. And then I have the minus 1. This minus 1 is actually going to shift this thing to the right. Now again, these transformations of the graph that's moving left and right, not really what we're focusing on right now, but what I want you to see is obviously the whole idea of the inputs and outputs. But overall, what is going on with an exponential decay function is that instead of the values growing, you'll see that the values are getting smaller and smaller and smaller. All right, our last example here, what we're going to do is just like we did in exponential growth, we're going to see if we can do the opposite, take a graph and try and write the exponential function based on the graph. So what we're going to try and do just like before is try and identify some points on my graph. So I can see a point here right at 0, 4. I see a point here at 2, 1. Heck, I even see a point right there at 1, 2. I see a point here at negative 1, 8. See if I find, oh yeah, right there at negative 2, 16. Okay, so just if I were to plot these points in my table, negative 2, 16, I got negative 1, 8, 0, 4, 1, 2, and 2, 1. My goal is to try and write my exponential function in the form y equals a times b to the x. So b is going to be my initial, a is going to be my initial value, and b is going to be my multiplier. The multiplier I think is easiest to see because we can see here my value here on the left side, I have 16. Then it goes to 8 to 4 to 2 to 1. So if I were to ask you what's going on with those outputs, I can see here that my outputs are being divided by 2 every single time. Now what I want you to recognize here is that when we write our function, we don't write divided by 2, but instead what we're doing here is we are multiplying. So this is where exponential decay is slightly different. If I want to multiply by some number to make them divide by 2, that means I need to multiply by a number that is smaller than 1, but also bigger than 0. So it has to be between 0 and 1. So what number would I multiply by that would be the same thing as dividing by 2? And hopefully you guys recognize that that would be the number 1/2. Cutting something in half is like dividing by 2. Now where are we starting from? We're always going to start by looking at the value where we have x equals 0. My a value, in this case my initial value, is simply going to be when x equals 0. So in this case my a value is going to be 4, so plugging that in I'd have here 4. So my function would be y equals 4 times 1/2 to the x power. And again, it's an exponential decay because our b value is going to be less than 1. So again, this was all focused on graphing exponential decay functions, looking at how the values are getting smaller and smaller.